Hello, this video will help you understand problem number 31 in chapter 5. For problem number 31, they are asking you to calculate the acceleration due to gravity near the surface of a hypothetical planet that has a radius of 1.5 times that of Earth. So, this is the first type of the homework problem where you're actually going to be drawing a diagram that's not a free body diagram. Most of the diagrams are actually going to be looking like the one we're drawing right now. We're going to have a circle, the radius there, and I'm saying this is Earth, so this is ME, and this spot here, this dotted line I'm drawing, that's R with a subscript of an E. And then I have a slightly larger planet, there. And they say the mass is the same, so I'm still going to label it as MP, but I'm going to write down that MP equals ME. And then RP equals 1.5 of RE. Alright, let's see, what else am I missing here? We're looking for the acceleration for the planet, so GP is what I'm looking for. So I'm going to go ahead and box that so I remember. Well, we can know that the acceleration on Earth will be 9.8 meters per second squared. And that looks like that has everything we know and everything that we should need. So at this point, you guys might be stuck, which is a little understandable because you're probably trying to just use the force of gravity with the universal gravitational constant. So you're most likely looking at this equation. Fg equals capital G, the gravitational constant, and normally it says m1, m2 over r squared. But instead of using m1, m2, we're going to say Fg equals the gravitational constant times the mass of the Earth and the mass of an object. We don't know what object, doesn't really matter. And then divided by the radius of the Earth squared. I do the parentheses and square just so that way you know E is a subscript. It will just be that one value. But this equation by itself is not enough. We actually have to use the old equation from Newton's second law, Fg equals mg. But we're going to also use this in the case for Earth. We're going to have mo. Now keep in mind, yes, this is the case of Earth, but this m that we had from Fg was talking about the mass of the object, so that's mo. And then g is going to be the acceleration on the Earth. So we are going to set these equal to each other because we know that's the force of gravity on the Earth for both of them. Actually, I should have added, this is Fg Earth, because it's not true of any other location. If we are using, that's not what I wanted. I wanted this. If we're using Earth here, and Earth here, and here, then this is only true if you have the force of gravity of the Earth. This wouldn't be true for the other planets. Okay, so let's go ahead and set these equal to each other, see what that tells us. So we have mo for the mass of the object times ge equals g was the lowercase g because it's the acceleration due to gravity, not the gravitational constant, but it will equal the gravitational constant multiplied by memo, is mass of the Earth times the mass of the object, and then the radius of the Earth squared needs to be divided on the bottom. Right away you should see that the mass of the object cancels out, which is good because it's not actually a value we had. And so we see, and this is an important relationship. GE equals, so the acceleration due to gravity equals the gravitational constant multiplied by the mass of the Earth divided by the radius of the Earth squared. Okay, so I used to say multiplied by the second mass. So I'm going to do it one more time. We have the acceleration on Earth will equal the gravitational constant multiplied by the mass of the Earth divided by the radius of the Earth squared. Now this is important because you already know this number. That's this. This whole time you've been using 9.8 meters per second squared. You're actually using the value. Circle it in blue. You've been using what this value equals. Okay, so that circle in blue is your 9.8. Okay, you just proved it. Now, that might be useful. You can pretty much be guaranteed it's useful, that's why I'm showing it to you. But that's not the only thing that you need to be able to understand from this. We now need to look at a similar equation using the forces looking at the planet. Now, with this green here that we had looking at everything on Earth, if we just change all those E's to P's, the equation still works. So instead of doing that, I'm just going to show you over here. We'd have mass of the object times acceleration on the planet equals the gravitational constant times the mass of the planet times the mass of the object, all divided by the radius of the planet squared. Okay, all I'm doing is changing all those green E's to P's, and then this equation still works. So the mass of the object still cancels out, which is good. And then we have a bit of a stop. We have, okay, gravitational constant times the mass of the planet divided by the radius of the planet squared. Okay, now to go further, we need to substitute the values that we know. So we are going to say MP is actually ME, because it says so right here. And I'm curious if I change this pen, does it change the whole thing? Let's see. RP, we're just going to substitute out for this 1/2 RE, or one, not 1/2, 1.5 RE. Oh cool, it goes back. Nice. So let's go ahead and do that. So this would end up saying the acceleration on the planet will equal the gravitational constant times the mass of the Earth, because I'm substituting that out, the mass of the planet out for mass of the Earth, and then I'd have 1.5 the radius of the Earth squared. Okay, pretty useful. At this point you could be plugging values in and say, okay, I know the gravitational constant, I know the mass of the Earth and radius of the Earth because that's in your book, and you could go ahead and go forward, but that would be a waste of time. You can just do this. You can say acceleration on the planet equals gravitational constant times the mass of the Earth divided by the radius of the Earth squared, and all of that will be times 1/1.5 squared. I just split the denominator, and so all of this is the 9.8 I talked about, right? It's the same as this, which means it's the same as this. So we can very simply, I'm going to go up here now. So I'm going to go up here, and I'm going to say G P. That's not a very nice P. There you go. GP is just going to be 9.8 meters per second squared divided by 1.5 squared. So you get GP equals 4.4 meters per second squared. And that's all there is to it. As long as you can identify how to substitute out the force of gravity, it should be pretty straightforward. This section here, understanding what I circled in blue, which now I'm going to, can I switch the colors? See if that works. This part right here I'm circling in red. Very important, very useful to remember. Okay, not on your equation sheet technically, you'd have to solve and show it, but it's very helpful and efficient if you can remember that the acceleration on Earth is equal to the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. That's very useful. Okay, you're going to see it multiple times in your homework. So that's on purpose to help you guys learn to memorize it, or at least to make sure you really understand how to do it. If you don't memorize it, you can easily work through the math and isolate it for yourself. You saw it only took 2 steps, maybe 3, in order to figure that out. Okay, so that's it for this one.